Next up, we have Dr. Helena Vitasova. She's going to be speaking about GRASS7, some new features and tools for spatiotemporal analytics and visualization.
Thank you. Thanks for introduction. We just got GRASS7 released last week, so I will be showing you some of the things. We have been using it for years, so it's not as new for us, but hopefully I will be able to show you some new things. Oh.
Tell me when to shoot it. All right, let's see.
It was working.
Well, it's still going. Let's see if we can go to slide 2. Try that. There we go. Hey, now it's working.
I got it.
Yeah. So what I'd like to present to you is GRASS GIS as geospatial research platform. GRASS has a lot of history with research, and it is just continuing in that direction. It can be, here I'm trying to describe like you can use it in different ways. So it is, everybody knows it probably as general purpose desktop GIS. The new release has new updated graphical user interface. But it is also used a lot for backend processing in different applications, in QGIS, in R statistics, but also for WebGIS applications. So you may not know that you are using GRASS, but you may be using it. And it has become a powerful geospatial processing engine that supports 2D and 3D rasters and vector data. But what is really nice about it, for example, for me as a faculty and instructor, is that I have everything in a single package. There are add-ons, but the core of the software is in a single package. And another important thing, it's a mature software. It has 30 years of development in it. So the core modules are well tested and well established. GRASS7 is being released as Spatiotemporal 3-dimensional GIS. So we have been using, if you have heard me before, I always show some animations. So we have been doing dynamics, but now it is much better supported through the temporal framework, and also the volume support, the voxel model support has improved greatly. So what you are looking at here is the simultaneous animation of topography on North Carolina coast. So this is 2D, 3D, and that's volume. That's volume modeling, and we are essentially browsing through the soil moisture data. So we have the temporal framework is there to support the management of large, massive time series. Then we have 2-dimensional and 3-dimensional visualization that you will see more of later on. Another thing that has brought new developers actually is PyGrass. It's a Python interface to the GRASS-C library, and what we are hearing is that it's very easy to do add-ons in PyGrass. So we are looking forward to see more sophisticated modules in GRASS thanks to this. Also, GRASS7 was released to couple GRASS7 release with R. Again, many people are doing geospatial applications with R. And as I mentioned, in addition to the core modules, there are many and ever-growing number of contributing add-ons. So here is a little bit more about the space-time framework. Essentially, a new time series data type was introduced where you have your 2-dimensional rasters or 3-dimensional rasters or vector data time series all managed in a temporal database. So you can use these database tools to manage huge time series that have thousands and thousands of rasters or vector layers. And in addition to this, to the management in this database, on top of it comes entire series of new modules. They are called T-dot modules that allow you to do all kinds of tasks and analytics on this time series. So instead of writing your scripts as we usually had to do, now you have these modules that allow you to do, to manage the data and to analyze your time series of data. Just a little bit of example here. This shows the time for which you have the data. Let's say your raster data with temperature are nice and continuous, but some precipitation point data really have some gaps in it. So you can nicely go through your data and look at where you have some holes in the data, and if you want to do some modeling, where you need to do, let's say, some interpolation, some gap filling. And this is just a screenshot of animation tool that allows you to create animations quite effectively. Here is one application from our colleagues in Italy, where they have processed huge number of MODIS data to create daily temperature time series for the entire Europe. And this is being like many people are deriving time series of temperatures from MODIS data. What is special about it? That they have used very sophisticated statistical methods to fill in the gaps, which are quite common in MODIS data, to incorporate the impact of elevation, distance to the ocean, and other variables. And they have it now set up as a nice tool, so they have computed it also for the United States. It's not validated yet, but they were able to do it. Here is another very interesting application where you may not know that you are running GRASS when looking at this data. There is a Spatial Informatics Laboratory at the University of Cincinnati. I very much encourage you to visit their website. They have developed several tools for analysis of topography and land use land cover and land use land cover change. And now they have even added a diversity, population diversity. And essentially what they do, they provide these tools as an online application. So for example, what I'm showing here are geomorphons. It's a new way how to depict and analyze landforms. So it has been done for the entire United States, and you can find the distribution of landforms for the entire United States at pretty high resolution. I think they are using 10-meter resolution. Even more interesting is Landex, which I don't have a screenshot here. What Landex allows you to do, but with geomorphons, some of the applications allow that you to do as well. You can pick up, you want to know where in the United States you have the same pattern, let's say, as here. And what it will do, it will analyze your little square that you put there, and it will find every area in the United States that has the same pattern. And it's pretty fascinating when you do the land use. So I looked at the Raleigh, like where in the United States are other places that look like Raleigh. So you can do that online. They also have similar for land use change, so you can analyze like where are the other areas that change in the same way. Pretty exciting. They, of course, it's massive computationally, and it's running GRASS, and they have written their own modules to do this kind of processing. Now, for the space-time framework, of course, if you have this time series, you want to look at them. So it was very important to get easy-to-use visualization to support the time series. So now when you have your data registered as time series, you can visualize them in 2D and 3D simultaneously, And if you have irregular time step, the time step will be honored. So if something moves slowly, you will see it moving slowly. It also supports the space-time cube visualization. And essentially what space-time cube means is that you are using the z coordinate as time. And I will show you later some application of that. So this is, for example, the visualization of Jockey's Ridge, of the evolution of Jockey's Ridge. I keep showing it like each time when I give a presentation I show it. So some of you might have seen it, but this is new, it has 2012 data in it. So I always add additional year. So you can watch it. You can watch how it is falling apart when you look at 2012. So this just shows the three-dimensional visualization of evolving landscape. And you can see it goes from one hill to three ridges, and those ridges are starting to fall apart. So for example, you want to know at what elevation is the dune starting to fall apart. So we put this set of raster maps, this set of digital elevation models into a voxel model. And then we extract a contour as an isosurface. And what you get then is something like this. So in this image, or in this animation, we are going through the time and we are looking at 16-meter contour and 20-meter contour. So we are looking at how these contours evolve over time. So it was just one contour in 74, and as it started to fall apart, you can see, oh, that was somewhere around 2007, it started to fall apart. So, and you can also see where it started to grow. So there was nothing here, and then this year it started to grow. Here it started to grow as well to 20 meters. So that's another capability which is geared more towards the research and analytics. Then we have this fantastic facility in Hunt Library. So we can take our data and we can bring the data to 270-degree visualization room, and we can explore our data there. So you can see how it looks like there. Now, another thing that is much better supported now with GRASS7 is spatiotemporal modeling of processes. So for example, here we have a simulation of surface runoff. This is for balsam mountain development in North Carolina. And because this is a very high resolution data, it's based on LiDAR, we need a very robust flow solver. So we are using this path sampling method, and this is just an illustration of that method. Now, where it has become really useful is when we have just started to work with the data that are collected by unmanned aerial systems. There is, I think, parallel to this, I think there is a discussion about all the policies and issues related to UAS. Here you can see the demonstration that was done just a few weeks ago near Lake Wheeler Road in the fields of North Carolina. And here is the resulting digital elevation model with orthophoto, which was processed by Justyna Jezdrowska, my visiting student from Poland. And here is the water flow simulation. And when you look at this, this digital elevation model is 15 centimeter resolution. The orthophoto is 3 centimeter resolution, so it's very high resolution data. And what you can see on it, what it actually captures is the tillage. And tillage is, if you are in agriculture, tillage is a pretty big deal in agriculture because it controls water flow. So contour tilling is, of course, an important conservation approach. And we can very nicely, with the path sampling, we can very nicely capture that this tillage is actually capturing water and it slows it down. And so here is another set of applications, modeling of dynamic processes. For Centennial Campus, we are using this data set in our courses. It has been captured by LiDAR. In 2001, that's the statewide LiDAR. In 2013, we got the Wake County LiDAR, very good data. So this is the 2013 LiDAR digital surface model. Here they are overlaid. In GRASS, you can do the cutting planes, so you can overlay the bare earth with all the buildings and canopy. Then you can run water flow on the surface. This is a very interesting application, very useful one that shows the solar radiation dynamics. And this is during the summer solstice, so that's when you are getting the most sun. With the LiDAR data, we get all the buildings, we get all the trees, so we can see and model and predict the cast shadows and the amount of radiation that incorporates also all these buildings. So for example, if you wanted to design a trail or design a path between these buildings and the library and you want it to be in a shade, you can identify where you need to put some additional trees for the summer. So that's summer, and you can do it for every day. You can do summaries and things like that. Here you can compare the summer solstice and winter solstice, so you have much longer cast shadows, shorter period of solar radiation. Here is fire modeling. Again, because we are in GRASS, we have lots of different modules. One of the modules that was modified to incorporate more dynamics is the fire simulation modeling. Again, here we are using the LiDAR data to create the surface model. So this is as it is now. And the front image there. There was supposed to be a brake line. Maybe you can show it. Are you showing it? You're not showing it.
No.
Okay. All right. So here is the Centennial Campus in the library. Again, you can see all the detail in the high resolution data. Same thing. And tangible landscape, I probably don't have to talk about it too much because you can see it, you can play with it in the exhibition hall. Just an overview. This shows you how it looks like in the lab. So we have several systems. We have 3 or 4 of them, so the students can come in, they can build their models, they can run different applications on it. So this is landscape architecture students. And I will just conclude with some information about our laboratory. So we are open source geospatial research and education laboratory at North Carolina State University. You may have heard about the Temporal initiative. So we are part of the worldwide network of open source laboratories. There is 91 of them now, all distributed all over the world. And we are, as you have seen, we are focusing on 2-dimensional and 3-dimensional data processing, modeling landscape dynamics. I have now the most active GRASS GRASS developers in my group. So I'm very proud of it and very happy about it, of course. That's why I can show you all the fancy stuff that we have here. And another topic that we are really involved in and that you have seen a lot of is visualization and tangible modeling environment. One thing that may be useful for you, on our website we provide access to all our courses. So if you want to find out how to do something in GRASS, you may find some of that here. Of course, I can't cover entire GRASS in my classes. And we have also some presentations, so you can see, for example, the presentations about tangible landscape and some of the other GRASS tools there as well. And I would like to stop here. So I will finish it with that. I have one slide about how GRASS is great.
That's it. No.
questions?
The tangible landscape work. What's the price point? What is
Price
it?
point?
Yeah.
There is no price point. Or the price point
How
is
much
like,
it
give
cost?
us some nice grant, then we will build it for you. Yes.
Well, so there's the hardware side and there's the.
Oh, yes.
Yeah.
So hardware side is now very cheap because I didn't talk about it, but now for scanning we are using Kinect. We used to use laser scanner. So laser scanner was 40,000. Kinect, everybody has Kinect. So that's very, very cheap. And you need a projector. And that's it. Computer, good computer. You need to have a good graphics card. And you need to have a software. And the software, I think it's all free.
Yeah, so GRASS is open source, right? So you can have it. The software which we develop is also open source.
The
And
SDK for the scanner is like you can download it.
so that's free.
So if you have.
2,000.
Like one of the things which is expensive are the stands. So if you go to
That's just a couple $100.
we have
Yeah.
stands there. If you can make this thing from wood, it would be perfect.
Yes,
You
yes.
have to put there the project.
Yes, the picture that I have from the lab that shows it, and we have been doing all kinds of setups. Here we have the projector in the ceiling, so you can use regular projector from the ceiling, and then you have nice large area that you project. And here is the stand with the scanner. You have seen it in the exhibition hall. And this is more of a setup that's in the exhibition hall, which is using the short throw. And then you have, of course, the models. You can do the models from the sand that you can try there. But we also use CNC routing. That's a little bit more expensive. And we also have used and experimented with printing. But the sand is really good. Yes.
Do you have any words to say about the increase in scalability with GRASS7?
Yes, so GRASS got better at working with very large data sets. And it's very important for LiDAR data. So you can now import LAS files directly. You can rasterize them. Like Doug Newcomb here is the master of running the largest. Then huge rasters. You can work with huge rasters, but one very, very important improvement was in vector data technology. So the management and processing of vector data got much better. Thanks to Marcus Metz. He is really a genius in getting things running faster. For example, for Arnold watershed, for the flow accumulation, basing, stream network analysis. For large data sets, the module now runs 1,000 times faster. So it was like it would run days, now it's minutes. So he does a really, really great job in making the modules and the data structures much more efficient.
All right.
Thank you very much. Next up, we have Randall Hale, going to speak about QGIS.
Yeah. Can you talk about your drive up here?
I could.
You want to get off of that computer?
Could I do that?
Sure.
Okay. Yeah, so let me tell you about leaving at 2 in the morning and driving up here. The word idiot is thrown around loosely. Let's see if this works.